What's up, chemistry class? Welcome to another lesson. This is the next lesson talking about light and quantized energy, right? So the first video you watched last week, hopefully, was about the wave nature of light. Then this video is about the particle nature of light, and the next video is about the dual nature of light, so how both natures play into the way light behaves. Okay? So I took a photo of the board there, Lonnie. So you can look at, I'll send it with when I send this video. So you can look at the photo of the board because you said that helps you, which I think is good. Absolutely, I'm glad you said that because I think that would help me too, looking at the board. I try to take the most important things from every system and write them up here, okay? So today we're talking, so after the lesson on wave theory, right, there were some things, people started looking at light and the ways it behaved. The ways light behaved didn't always fit exactly in wave theory. So people started looking for other theories and other ways to explain light too, okay? So these next couple things are confusing, but basically what you need to know is that the way light behaved didn't fit exactly in with wave theory. So that's where they came up with particle theory, okay? Look. All right. So the wave model of light couldn't explain why heated objects emit only certain frequencies of light at a given temperature. And it also couldn't explain why some metals emit electrons when light of a specific frequency shines on them. That's called the photoelectric effect. We'll talk about that in a second. But basically, when heated objects emit only certain frequencies of light at a given temperature. So basically with wave theory, things were predicted, it's hard to explain, but things were predicted to behave differently than these two examples. So with the photoelectric effect, it was predicted to behave differently. I'll talk about that in a sec. I have a drawing to explain the photoelectric effect, okay? But basically, wave theory predicted light to behave differently than it did in some instances, and that's why they came up with particle theory. So scientists looked into a new method of light, and what they called it the quantum concept, what they found. And what they found is when objects are heated, they emit glowing light, okay? When objects are heated, they emit glowing light. So the example in any system is a very good one. Iron gets hotter. So when iron gets hotter, it gets brighter. And it has more energy as it gets hotter, and then it emits more light, different colors of light, brighter light, okay? That is the example that they used of the quantum concept. When energies are heated, they emit glowing light, okay? So when the iron is hotter, it's brighter, and it emits more light, okay? Okay, so that leads us into Max Planck, okay? Okay, Max Planck. He is still looking for answers, okay? And what he found out that matter can only gain or lose energy in small amounts called quanta, okay? So atoms can gain or lose energy in small amounts called quanta. This is his theory, okay? But he had evidence to support it, okay? A quanta is the minimum amount of energy that can be gained or lost by an atom, okay? And this was disturbing. This caused trouble. It was disturbing because people thought that energy could be absorbed and emitted in continually varying quantities with no minimum limit to the amount. That's a big mouthful. But basically, here's an example to explain that, okay? So people thought, oh, if I'm microwaving water and I add a certain amount of energy, it's stepwise. So I'll add this step of energy and the water will heat up to that level. And that's it. But in reality, what happens when you microwave water, if you add more energy or less energy, it still heats up gradually. It's not steps. It's not boom, 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 boom. It's just gradually. The water gradually heats up, okay, in little tiny steps. But those tiny steps add up to just it gradually heating up, okay? So basically, there's small amounts called quanta, which is different. The wave theory was like bigger steps. Like, oh, you hit this step, ka-chunk. You hit this type of energy, ka-chunk, but the particle theory was gradual, okay? And that's where the quantum come in. Small amounts called quantum. A quantum, remember, the minimum amount of energy that can be gained or lost by an atom, okay? So, that leads us in to energy of a quantum, this equation he came up with. You will see in the next video, Einstein modifies this equation a little bit, okay? But it was introduced first by Planck. So we have here E quantum, which is energy, okay? And equals H times frequency. H is Planck's constant that he came up with. He came up with this number, okay? And then, remember this funny looking V thing is frequency, all right? Yeah. So the equation shows the energy increases as frequency increases. So if we look here, right, if this number gets bigger and you multiply it by this number, the energy gets bigger. So more frequent, the more frequency of the quantums, the more energy there is. Okay? And this number that he came up with, he did a bunch of tests to come up with. That's all really confusing stuff. But basically, he came up with this number, 6.626 times 10 to the minus 34 joules per second. And joules times seconds. Sorry, joules times seconds. And a joule is a unit of energy. Okay? So this is energy. This is energy units. 6.626 times 10 to the minus 34 joules per second. Okay? And that is the equation that he came up with for energy of a quantum. Okay? Let's make sure I'm not forgetting anything. Hopefully you guys are tracking with this. You can rewind or check on every system. Okay? So the equation shows that energy increases as the frequency increases. That's very important. Planck said that's the next thing we'll talk about. Okay? So basically, Planck came up with the idea that matter can only gain or lose energy in small amounts called quanta. And a quanta is the smallest amount of energy that can be gained or lost by an atom. So instead of steps, it's little quanta. So that means it can gradually gain or lose energy. It doesn't have to have a big boom drop. Okay? And then he came up with an equation to calculate that. And now we'll come over here. Okay? So, Planck said that matter can only emit and absorb energy in whole number multiples of hv. So we have our equation, right, which was over here. Can you still see it? Yes. We have our equation, which was E quantum equals hv. So he said whole number multiples, which means 1 hv, 2 hv, 3 hv, 4 hv. You cannot have 1.5 hv. You cannot have 1.76 hv. It goes up in whole number intervals. Okay? It has to go up in whole number intervals. And that's what he found based off his research. So what that means, to like compare this to something that you can see, right? Look at these blocks. That's better on the side. You see these blocks? Can you take off half of a block? If you want to remove this block or add a block, you have to add a whole block. Oh. I'm going to get a different marker. This marker's not working. Sorry. Okay, look. So, look, if you have, get rid of this. So you have a block. You want to add a block, or you want to take away a block. You have to take away or add the whole block. You can't just take away half of the block. Like when you're playing with the block, yes, you would cut it in half. When you're just playing with them, you have to take off the whole block or put on a whole block. This is your only option. So that's what he said. It's only whole number multiples of hv. Those are the only options. So you take it off, and that's the packets of energy, the quantum packets of energy. So you can only take one packet off at a time. You can't cut the packets in half. That's why 1, 2, 3, 4, 5, etc. Right? You only can take it off in whole number multiples. Whole number multiples. No halves. No halvesies. Okay? Alright. No halvesies. So, that being said, that leads us into the photoelectric. Okay? So, this is part of why this can be explained by quantum theory. Okay? So, the photoelectric effect is where electrons, called photoelectrons, are emitted from a metal surface when light of a certain frequency or higher than a certain frequency shines on the surface. One more time. Electrons, called photoelectrons, are emitted from a metal surface when light of a certain frequency or higher than a certain frequency shines on the surface. So in any system, you'll see this, when you look, you'll see this piece of metal. And these little dots in here are all electrons. I know I'm not a very good artist, okay? But the idea was, so what happens is the light beam hits the metal, and electrons leave. Photoelectrons leave when light hits the metal, okay? But what happens, wave theory predicts that with energy, with enough time, any type of light would supply enough energy to eject photoelectrons. So that just means no matter what the frequency of the light is, if it hits the metal for long enough, electrons will start to leave. But that turns out to not be true. Well, you can have like a low frequency of light and it hits forever. The electrons will never leave. So particle theory says that the light must be a certain frequency in order to eject photoelectrons. So it must be at a certain frequency. It must be at a certain frequency, more frequent. It must be at a certain frequency. The light has to be a certain frequency. I keep saying that over and over. Okay? Light has to be a certain frequency in order to eject photoelectrons. They will not leave unless the light is a certain frequency, which is counterintuitive to wave theory. Okay? So, no matter how intensely or how long the light shines, so here's the example that they have on incident is with silver. Okay? So no matter how intensely the light shines, light with a frequency less than 1.4 times 10 to the 15th hertz doesn't eject photoelectrons from silver. But, however, even a dim light with the frequency of 1.14 times 10 to the 15th hertz will eject photoelectrons. So it doesn't even matter how strong the light is shining, as long as the light is the right frequency. So it's all about frequency. If the light is for the example of silver, if the light is 1.14 times 10 to the 15th hertz and it hits the metal, it will eject photoelectrons. But if it is less than that, it does not matter how long or how bright, how strong the light is, strong or dim, it doesn't matter. It will not eject photoelectrons. But if the light is 1.14 times 10 to the 15th hertz, it will eject photoelectrons because it is strong enough to eject photoelectrons because it is at the right frequency. So wave theory said, right, that any type of light shining on the metal will eject photoelectrons, but that is false. Particle theory says the light must be a certain frequency in order to eject photoelectrons. Okay, and that is what it tells us. So this is kind of confusing. These are very tricky concepts, okay? So I'll try to tie it all together in the next video about the dual nature of light and how it ties together and what Einstein did. Einstein took the wave nature and the particle nature and he put them together to explain the way light is as we know it today, okay? So I know this was pretty confusing. This is just a confusing concept. I'm sorry it's confusing. Okay, but it's important to understand the dual nature of light as we look at the behavior of electrons and how they affect chemical behavior. Okay, all right, next video will be on the dual nature of light in a second.